I was informed to give a talk on fairly short order, so this is a reused talk, but it's called Lessons from Metamath, and the idea is that this is a talk for people who don't intend to use Metamath, to find out like what sort of things does it do, and why are those interesting? Why should you maybe either build this into your ITP system or complain to others to build it into your favorite ITP system? Okay, and this is in memory of Norman McGill, who is a good friend who died in 2021, and he created the Metamath language. So Metamath is a computer language for verifying mathematical proofs. So we've already seen several of these in this week. It's also a program called Metamath.exe to verify proofs, and it's also a library of completed proofs. These are in a wide variety of mathematical systems, but the biggest one is set.mm. This does a bunch of theorems in ZFC set theory, and so this has a bunch of interesting theorems from a bunch of different areas, we saw it previously on Frake's list of theorems. And so there's also other, so you can see from the numbers, you can see from the number of proofs, generally the relative sizes of these things. You know, set.mm is the biggest one, set.mm is some proportion of that, and then there are others doing things in more obscure logics like quantum logic, and there's also like higher order logic, dependent type theory, piano arithmetic, and Hofstadter's MIU system, which is a fun application.
Oh, dependent, not displayed, I like.
Yeah.
Do you know how many proofs are in the MIU?
One, I think. It's the one that's in the paper, right? Or in the book, yeah. Or well, actually, no. That one's a non-theorem. That's actually.
Oh yeah.
So it has the example of like the proofs that you can.
Proving that would be hard.
Yeah. So this is just the theory itself, the things that you can derive, but you can't do meta theory in this sort of thing. You would need a different formalization in order to do the meta theory thing. Anyway. So if you open up a Metamath file like set.mm, yes, this is one file. You can see line 66,000 contains theorem about functions with domains. So you probably look at this and you say like, what is this? Like, this is crazy, right? But it does break up into some pieces. So like, this is a statement of a theorem. This is a comment that describes the theorem. One of the things I like about Metamath is that it actually requires comments on every theorem. This is a very useful way of getting people to actually say what they're doing. And these are hypotheses for the theorem. And then this funny business here is a compressed proof script well, okay, maybe I shouldn't say proof script. Is a compressed proof term of the theorem, and there are other ways of viewing that. This is MMJ2. This is a proof assistant for Metamath, so people don't actually write these lines themselves. That would be.
I fully expected that in 2015 you would have been able to do such a thing.
What, that you would be able to write those?
That you would be able to.
No, you. Your name.
So I have written tools that write this, but I generally try not to do so by hand.
Is it Unicode? I see an equal sign in it.
No, this is not. So this is an ASCII file. Oh yes, I have a programmer font, so it does nice things.
Have you ever written one such compressed proof?
I have written very small ones for testing purposes.
Looks like base 64.
Yeah, it's actually encoded using like it's all capital letters on purpose, you know, the A to Z on purpose, so that like when you grep through the file, you won't find random hits in this, because the theorem names themselves are all lowercase, so it makes it easier to do find and replace theorem renames. Okay, so the way that people actually write proofs is using something like this. So MMJ2 is a Metamath proof assistant. It's not the only one. This is another interesting aspect of Metamath, is that it does not have a single proof assistant that monopolizes the task of producing proofs in the theorem. Neither does it have a single verifier for processing these files. I'll mention that later. So this is proving that 95 plus 1 is 96, and you can't see it here, but this is actually generated by some automation that's in this tool, and it will produce a sequence of, so these here are names of theorems, and they're all being put together, and then I guess you can't see it here, but just below here you would see the outputted sequence of all capital letters and whatever that you put into the file. This is the Metamath Proof Explorer. This is a website that you can go to actually see these theorems in a more readable form. These are all hyperlinked and so on, so that you can investigate the library. This is the way that most people interact with Metamath. Even if you're working on Metamath and you have the file, it is still nicer to be able to generate these HTML files and click around and understand what things are. There's things here telling you like what do all of these, you know, what does the symbol mean, and then you can go to the definition and find out.
So can you do it on the fly as you are writing your MMJ2?
MMJ2 does support being able to generate these. So
I love that it starts with like the real numbers are in the universe.
yeah, well, I mean, it's set theory, right? So you have to prove at various points that things are sets in order to apply theorems, because we also have sort of class variables. So you have to distinguish between the proper classes and the sets.
So it's not ZF, right?
It's actually a conservative, you could say it's a conservative extension of ZF to support sort of predicate, you know, these are essentially syntax for predicates with a designated free variable. That's the idea. So, yeah.
And there's the colors.
What? The
Colors of the numbers.
the colors of the numbers. Oh, these.
Yes, yes.
Oh, yes, you can see that I visited the axis. You're probably talking about these. Yeah. Okay, so the idea is that the numbers that are smaller there's some rainbow coloring, and this gives you some vague sense of like how complicated a theorem is, but by its ordering in the file. So, okay, so as I said, my goal is not to convince you to use Metamath. It's to focus on what Metamath does differently. You know, compare it with if you've been looking at some other system during this week. I want you to think about what this is doing and what your proof assistant is doing, and maybe whether these are good ideas or whether there's some way to combine them. I'm also going to tell you about Metamath 0 somewhat. So Metamath 0 is a proof assistant that I've been working on based on essentially me doing these two things. So I looked at Metamath, I looked at the the system I'm using, and I say, it would be nice if I had Metamath but with these extra things, right? And so I built a system that has Metamath and some nicer things, and I'll show you some of that as we go along. Okay, so there's three main ideas I want to mention here. One of them is to separate proof authoring from proof checking. Another one is to have a simple spec for the logical core. And the last one is this notion of direct substitution. And I'll explain more about what these are. So interactive theorem proofers fundamentally need to support two different activities. One of them is writing proofs, or operating proofs, and the other one is checking them. The design criteria for these are completely different, and it's important that we recognize this. Writing happens once when you're trying to figure out how to prove a theorem. Checking happens many times. It gets checked into some CI, and then it runs all the time. every day, it gets integrated and whatever. Or on everyone's machine when they download your system and then they want to interact with these proofs in some way, they might want to check it. So checking is often performed as part of CI. Writing often involves human interaction and creativity. So for writing, what you need is a proof assistant, a thing that helps you build proofs. For proof checking, what you need is a kernel. You need something that is small and understandable and has very little moving parts and is very trustworthy. So a good proof assistant should be big and complicated because those are the things you need to power these human-computer interaction features. For a good kernel, you want the opposite. You want it to be small and trustworthy. And ideally, you want your kernel also to be fast and not resource intensive. This is important for scalability. If you want to be able to do big proofs, you need the kernel to be able to handle that. So having a kernel which is too simple might cause it to also be too slow, and then it won't be able to get to, whatever big landmark theorem that the user is aiming for. The way that Metamath accomplishes this is through the crazy garbage over here. It stores proofs, not proof scripts. This is not an encoded version of SIMP. This is an encoded version of the actual proof, the proof object. As a result of this, checking Metamath proofs is massively faster than checking Lean or Conk or Isabelle or Whole Light, because all of these systems contain these proofs, and those are the only things that are stored. And because of that, if you want to check the file, you have to rerun the proofs. And if it's doing some kind of search procedure or whatever, that's innately going to take more time than if you had just stored the proof term itself. So set.mm is a library of a bunch of proofs in ZFC. It is on the same order of magnitude as Metamath, although Mathlib, although Mathlib does keep growing, so I'm not so sure I can keep saying this. But it can be checked in about 8 seconds using the classic verifier, which is much less than the about 1 hour it takes to check Mathlib.
But what about the change management? I mean, the problem with the proof scripts is they break if something changes.
That's true.
And I think your proofs will break even worse if something changes.
So they will break better, is what I would say. They break in a very predictable situation, which is when one of these theorems, and only those theorems, changes its statement. So if you change the proof of any of those statements, nothing changes. If you change any theorem which is not listed here, nothing changes. By the way, this thing in the braces is actually the list of theorems that are referred to in the proof, so this is also very useful for being able to gather dependency information without rerunning Metamath. But in any case, if any of those things does change, then the proof will almost certainly break, and you can take the old version and the new version of the theorem and bring them into MMJ2, and then one line of the proof will be broken, which will be exactly the application of that lemma, and so the changes will be small and manageable. In many cases, they can also be automatable, although the support for that is not great.
What happens if you have more than 26 referred theorems?
So this, there's 26 letters, but Z is special, it's for back references, and of the other 25, it's actually it's a mixed base encoding where you have base 5 and then the last one is a base 20. This is a trick used for encoding variable length integers, and there was some analysis done over the distribution length, so what decreases the size least the most, so that's how it ended up as that one.
We need this 8 seconds checker. In what language is it programmed?
That one is in C.
Okay, so
This one is in Rust. This one is also in Rust. So I really liked this idea of being able to check things quickly, and I sort of redesigned this thing to not use letters and instead use binary and so on. So there's a bunch of tricks that you can do to make it do this but better. And doing that, I was able to do the same trick, but in Metamath 0 in 2 seconds.
I expected fake protests that you have Coq in the list because Coq has the .io files, which I think are proof objects.
Well, so the issue there is that Coq proofs are also sort of proof scripts. They have definitional qualities that they do not log, and so you can still do significant search inside a proof term. So that is a unique innovation of dependent type there, and it means that you certainly, so one of the properties that I was able to achieve with Metamath 0 is that the check time is essentially linear. It is worst case quadratic when you have like a statement which is half the size of the file. But if you assume that the statements are bounded in length, then it's linear time checking. Checking, lean, and Coq, the asymptotic complexity of that is one of the largest ordinals that I could barely gesture at being able to describe. It is very high complexity. Okay, so takeaways from this is you should cache your compiled proof objects. Even if you have a proof script, you should still keep hold of those proof objects and try to reuse them when possible in order to make things faster. Lean has oleans, Coq has DO. These are generally not usable for fine-grained caching because a lot of them have dependencies on, like they will break very often when many other things in the environment change. Polite and Isabel are in a particularly bad position because of this ephemeral proof thing that, that Frank was talking about. If you erase the proof as you're writing it, then you have no way to rerun that without rerunning the proof from scratch. So you really are forced to do the computation in that situation. So Metamath 0 doesn't do anything particularly special for this, but it is able to import precompiled files. I will show you some Metamath 0, but it does in fact have proof scripts for other design reasons. And so it also has a sort of similar situation to Lean where you probably wanted to cache this proof object. Second takeaway is to have a verifier-friendly format that is fast to check. I mean, Olean and VO are kind of that's the idea. But this is, I think, really clearly emphasized with the design of Metamath. I won't be able to go into the details of the binary format there, but it's really like laid out in such a way that the verifier has almost nothing to do. They just have to check that like every line is in fact an application of the thing that it says it is. And this is sort of what gives you this linear time property. So having fast to check things is useful for CI, it's useful for proof translation, it's also useful for auditing. So
that is something which is really independent of the humans, and it doesn't really matter how long it takes. Right? It's a background task. You can outsource this to somebody with a big machine, and you don't really care for the timeliness of all of that.
No, that is false. So, you might think that you don't care, but you do care once you hit the limits of your human patience or of the budget.
But those are all non-human things.
Yeah. Oh, yeah. I mean, so what I think is that Metamath innovates the most when it comes to back end of a proof assistant. So it's like, how do you manage these proofs? How do you check them? You know, a bunch of things that are sort of not really related to the user interface of a proof assistant. You can give a good user interface without really hitting on these things. It's sort of orthogonal in a lot of ways. But I think that like check time is actually a limiting factor. Like if you're, Mathlib was starting to push 4 hours to check before it switched to Lean 4. Like Mathlib is running CI continuously. It has several build machines. It's trying to support, merges several times a day. At some point, you just run out of time to compile things. And then progress slows.
Besides, it's not really sustainable from an environmental perspective.
And from an environmental standpoint, yeah,
And
if
also,
you
I
want to
think
scale this up
it
to
doesn't
everyone
take-
is doing it, that's a very costly endeavor now, right?
So one data point, I would like to check the KML development, but my machine only has 60 gigabytes of RAM, so
Yeah.
it doesn't work.
Well, that's something you can buy out of easily.
Oh, you
And
know?
The humans are the expensive things.
So this is true to an extent, but there comes a point where scalability hits, like, it actually becomes relevant, and I would say that the formal methods community is hitting that limit right now. We now need to cut back and make sure that we are doing things efficiently, because just not worrying about it is actually causing us real problems now.
If I
But
can,
I think the word they need to use, it's causing human problems.
Yes.
That's the point.
Exactly.
Yeah.
You have the point where it's causing human problems.
You're also
Which
keeping
I think this is what Michael is saying.
Yeah.
You are also keeping people away from using your system if it takes 4 hours to check. I won't use a system that takes 4 hours to check.
so
Maybe you don't want me in your community.
one analogy for Michael, which I find quite interesting with respect to what Mario is doing, is like 20 years ago, the Linux community was hitting these issues with all these legacy version control systems. And Torvalds actually gave a really nice talk where he claimed that doing version control right and fast in Git really had sort of a revolutionary / transformative effect on how people work with version control. So it seems to me that sort of Mario is going after a similar revolution in the yeah.
Yeah, I mean, these, you know, the differences in speed here are more than, you know, we're talking like 8 orders of magnitude difference in speed. This is more than something that, like, you can't get this by optimizing your thing better. This is really a design decision that has effects, and it changes the way, you can run this between key presses if you want to, right? This is something that you can run between key presses. Checking cock, not so much, right? This changes the way that you use the software.
A fundamental criteria in one software house I use is that it should take less time it takes to get a cup of coffee.
Yes.
Well, on the grounds that if it takes more time than that, your brain swaps into solving a different problem, and your human cache is destroyed.
Yeah. So in HCI, there are a bunch of like categories for like, okay, how much can you take before people start, you know, thinking about other things? How long can you take before, you know, it's time for a lunch break, or this has to run on a nightly versus, okay, let's get a build farm. You know, there's a bunch of layers where we have to deal with this, and ultimately this is just, it's not like those numbers are absolute. It's not always going to be those numbers. Those numbers correspond to the size of the library. But the thing is, people keep producing new stuff, and we want them to keep producing new stuff. And if they switch into one of these different categories, that changes the way they're using it, so they won't be able to go as far before they have to start taking coffee breaks frequently. Okay. And the other takeaway is to have a small trusted kernel, which several of the proof assistants here are doing. Side note here, like, that's not a good sign, right? You don't want your trusted kernel to be that complicated that it's difficult to understand. Another one is that external is better. I have a sort of fundamental distrust of in-process kernels, and most of the existing small trusted kernel systems are in fact in-process kernels. There are things that you can do to cause the big stuff to interact with the kernel in bad ways if you have, you know, undefined behavior, or if your type system is not super strong. You might not be able to prevent interference with the kernel in the process. So this is an easy way to add an additional barrier that prevents that sort of interference. Okay.
Sorry, just to add something, the Metamath book, I forgot the name of the author, he explicitly says that he wanted to design a system such that, like, any person that can make simple calculations could verify any proof in principle. Which it's a bit optimistic, but it's a nice sentiment, right?
Yeah. So the mechanism by which the proofs are checked is very easy to explain to a person and very easy to explain to a computer. This relates to a point that will come up later. One of the things I wanted to mention again about this interface is that this allows you to, I sort of already mentioned this, but like you can click on these links and you can explore a proof to any detail that you want. This is good for two things. It allows you to learn the rules of the logic just by like watching how it is used in situ, and it also lets you learn how the proof works without any required background. I think that this is actually kind of underappreciated, that like, to some extent you have to have the right mindset in order to approach these, but you can actually like go down to the levels where it's really just sticking like this into that is, there's not really anything going on, and you can take any proof you like, pick prime number theorem or something, and you're like, what is that symbol? And you could go there and find out what is that symbol, and you'll see a bunch of more symbols that you don't understand. You can keep going until you get bored. This is like a nice way to learn about how mathematics works. Not everyone learns in this style, but some people do. And I think that it's very nice to be able to have something that allows people to work in this way. And this is one of the major advantages. This is more than the 1 bit that Mike was talking about. This is, something else that you can get from formal methods. And I want to mention, as far as things that I've taken from this, in Lean there's a command called #explode that will basically produce a proof in this elaborated style for Lean proofs. And then you can click through these stuff.
Is that just display, or can you also check it in some way?
It's for display, yeah. I mean, the HTML up there was also for display, right? The checking is...
No, it wasn't a question, just a question.
So, yeah, this is really about how do you take proofs and make them understandable to humans, right? And there are lots of other things that you can do. Like this is showing essentially individual inference rules of the logic. So you can also think about like, oh, how do I find what are the important steps, right? And like I mentioned that the coloring there of the different things, like this is telling you, oh, Repelem 13 here is a relatively important theorem. This one is like just modus tollens. This is a boring theorem, right? So that gives you some sense of what's important and what's not. But it would be nice to have something that is a little bit more targeted. Maybe use some, I don't know, machine learning or something to figure out how to find what's interesting. And the zero docgen generates proofs in the style by default. I actually have an example for that. I forgot to. Well, okay, you can still see this. So this is a theorem about commuting existence and OR, and so this is my take on this Metamath proof style format. Here, there's actually some hidden lemmas because this is stating that equivalence is transitive, and you can collapse instances of modus ponens inside that. Another thing here is the way that axioms are handled. So you can always, so one of the things that you get in the Metamath Proof Explorer is you can see what axioms, like modus ponens, are being used in a theorem, like transitive. And so these get shown here. They're also collected into groups. I call these axiom sets. And they allow you to sort of see, because a lot of the time there will be many, like predicate calculus has, I don't know, 6 axioms or something like this, and propositional calculus is 4. You might want to hide those if it's not interesting and you want to focus on, axioms of real numbers or more interesting stuff.
And those spaces now to parentheses.
Uh,
Something Metamath space.
Yes, that's one of the small improvements is that you don't need to put the space around the parentheses. So makes things look nice. Okay. Second part is to have a simple spec for the logical core. So Metamath has a pro specification in the Metamath book. So there's a book that you can download that explains sort of the manifesto of like what Metamath is trying to do and how do you define what Metamath is. This is, it's written at a very like, it's not written for someone with formal methods background. So it's really like, okay, how do you put these things together? It's about 28 pages just to describe all the keywords and all of the parsing and all of the proof checking and these things, with lots of explanation and examples. There's an emphasis on parsimony. This is really like a minimalist language, in case you hadn't noticed. It is a language which is designed to be very simple for computers to parse. It's not optimized for humans, not really. It's sort of, it's good enough for humans, but it's really optimized for verifiers. One of the things that I like about this is that like, I guess here it's saying that like, there's these diagrams here that like explain, how does the substitution work? Once you understand that, once, you replace all the C's with an expression and then this theorem is being applied here. Once you understand this mechanism, you can understand every step of every proof in the entire system. So this is a very sort of powerful concept. It's essentially saying that substitution is all you need. So one of the consequences of this is that there are many verifiers, like a lot. There are 19 known verifiers in almost as many languages. So, a bunch of languages. There's even one written as a Turing machine, which I think is really awesome. This is,
How many states?
huh?
How many states?
I think it's about 2,700. So, if you try compiling, anything into Turing machine, it's quite difficult. But someone actually used this to prove a math theorem, which I think is super cool. They used a Metamath verifier, or a stripped-down version of a Metamath verifier, in order to construct a Turing machine that will enumerate proofs in ZFC and use this to prove the smallest unprovable in ZFC busy beaver number. So this is the busy beaver number where you cannot put any upper bound because the behavior of this particular Turing machine cannot be established to halt or not, because that would imply the consistency of ZFC. So many verifiers are tiny, some of them are fast, some of them, there are some that are reasonably fast and also small.
Which is the smallest?
I think I have a Mathematica verifier that's like 70 lines of code. It's in the range of like 300 to 500 for the average programming language. And as I mentioned, there are also multiple proof assistants. So I showed MMJ2, that's the one I'm most familiar with. There's also MMPA, which is sort of the original one. It's part of Metamath EXE, the one that Norman McGill wrote. There are actually, this is out of date, there's like 3 others in development. It's also been used for machine learning. So interesting application of this is that like since Metamath has simple rules, it's easy to sort of get lots of training examples and try to get something that predicts the next step. And there's like this GPTF system that was developed to produce Metamath proofs. This was later extended to do proofs in Lean. I think it does tactic proofs in that case. So sort of similar to tactician or these other things. Okay, so my takeaway from this is write a spec for your language. There are surprisingly many proof assistants that do not have a spec for their logical core, and I find this to be a terrible, terrible thing.
Impossible
Which
to
ones
crack.
do have a spec?
Which ones do have a spec? Good question.
Cop doesn't.
Polite has
Cop doesn't, Agda doesn't, Lean kind of, but let's not trust
Someone
them.
wrote a master's thesis.
It was just written by somebody for the master's degree, can we trust them?
let's see. So Lean mostly does. Lean 3 has a spec written by a certain master's student. Lean 4 added some things. Those are not yet reflected in the thesis. So there's some more work to develop that and prove some facts about it.
So Lean seems to be kind of as close as Coq maybe, because Coq actually explains in the documentation a bunch of things.
Yeah, I mean, certainly explanations of the type theory exist in most of these languages, but I wouldn't call the explanations a spec exactly. In particular, none of them are normative, as far as I'm aware. This is normative, right? There are 19 verifiers, and they're implementing this. Right? It's a reversal of, it's not you have this one implementation and whatever it does is the spec, which is what you usually see in these proof systems.
My implementation doesn't agree with the spec. Let's change the spec.
Yeah. I mean, once you have multiple implementations, a spec sort of comes out naturally, right? Like this is what happened with C. Like the reason why people clamor for a spec is once you have multiple incompatible implementations of kind of the same thing, and then it becomes a problem for like having them work together. So I'm pretty sure that this is a major factor in why most of these systems don't have a spec, because they don't need one, because they have a single implementation, and that implementation sort of is the spec, I guess.
Nobody's crazy enough to try to do it again.
Exactly.
Well, there was Coq and Tita.
They
diverged by now, but it started as a re-implementation of Coq, I think.
Yeah. So.
And Matita has a paper that's closer to the spec than Coq has.
Yeah.
But it's not complete.
Which is why I think that re-implementing the kernels of proof of systems is a good thing to do, and it's something that I work on in my free time. So as I mentioned for Lean, there are external verifiers, so there's some sort of competition in the space, but there's no spec. And actually, I'm not even sure about the competition business. Like a lot of them are not used in slowly decaying. So unless these things actually, stay working, they sort of lose effectiveness, right? I would say that whole life actually does pretty well in this front, especially because of the work that John did to prove the correctness of whole life with respect to some large cardinal axiom.
Romana did it better.
Oh, okay. And so I saw this, I was like, you know what, let's write the spec first. There's a specification for this language, Metamath 0, and then after that, the implementation is done. Another one is to support low-level proof translation, both import and export. Most systems don't do this at all. I think this is one of the main reasons for the sort of balkanization of the proof assistance. One of the things that can be done to improve this situation is to have some kind of proof translation between systems. No one really performs well. I actually already mentioned earlier in this talk that I have a proof of, or I can verify set.mm, which is a Metamath file in Metamath 0, which is a different language. In order to do that, I wrote a translator from Metamath to Metamath 0. You can import from Metamath, you can export to the whole system and to Lean.
Which whole? Which whole?
Generic whole.
Open theory?
It's sort of hull looking and sort of easily retargetable to a specific hull system. Because exactly of this situation, there are like 6 hull versions, like which one am I going to target, and is targeting one specific one going to prevent retargeting later?
But it does whole life.
Huh? It does do whole life. Okay. The last one is to use direct substitution. I'm not completely like on board with this one, but like I'll explain to you what this is. So Metamath uses a particularly simple form of first order logic. Sort of the origin story of Metamath was this paper by Tarski that explained that actually you can do first order logic using much simpler notions of substitution than the classical first order logic one.
The calculus of relation?
Hmm?
You mean the calculus of relation?
I don't think so.
No.
Tarski was in it, and it sounds like it.
I mean, yeah, so this, I can send you the reference if you're interested. Yeah, so the basic idea is that this substitution is essentially direct substitution. It's just you take all occurrences of A that you see in the formula, you replace them with 1 plus 1, that kind of substitution. If there are bound variable captures, whatever, just do it, right? So with this kind of substitution, you can run into bound variable capture issues. And then there's a second technique that's used to avoid that, which is there's a notion of a variable not occurring in a formula. So it's not about freeness, it's just about you look through the string, do you see an X anywhere? If you don't, then it's not there. So these are both very simple to implement in a computer. Substitution and disjointness, they are both like Turing machine activities, right, that you can do. With bound variable capture and other things, like it's a lot more work, right? I'm not sure that I want to completely connect this to the linear time checking, but it certainly makes it a lot easier to implement because you don't have to worry about expressions like being renamed or like having to do lifting in like the de Bruijn indices way. But yeah, so it's possible to do this sort of thing, and set.mm is a proof by construction that this actually works at large scale. Yeah, so if you can simplify the logical constructs the kernel needs to know about, this is good. This makes things simpler and sometimes faster. So I think that it's important to have ways for the kernel to sort of keep up with more advanced mathematics. The idea here is that if you can have more advanced theorems and use them in a certain way, you can avoid like having large theorems take a long time to check because they are actually like functions defined in terms of primitive inference rules, defined in terms of more primitive inference, or something like this, where the actual time it takes to run through all that code increases as you get more complicated. Like this is my general impression of like HOL is that like because it's functions upon functions upon functions, if you're not careful about it, like you're actually pushing a lot of primitive inferences directly through the kernel. Whereas in Metamath there is more of an emphasis on like, okay, let's make as much as possible into theorems and reuse those so that the actual size of the theorems stays human-sized. Right? So Metamath 0 sort of tries to do it both ways here. So it uses a subset of first-order logic rules that are compatible with both the classical first-order logic interpretation and also this Metamath interpretation just do. And so because of this, it can be straightforwardly translated to both. And as I mentioned, it doubles down on this linear time property. So I would say that Norman McGill did a great service to bring Metamath to us and show that all of these ideas are actually possible to do, not just in principle, but in practice, right? Tarski showed that it's possible in principle, but at that time, no one was writing systems to do this sort of thing. And now, like, we can see that this is actually a way to build a system. So even if you don't actually use Metamath, I think you want to consider how these kind of architectural decisions can affect like the turnaround of your CI by orders of magnitude, right? The trustworthiness and the replicability of the language rules, and also how tightly coupled the proof assistant and the kernel are, or whether the proof assistant features cause pressure on the kernel to grow. What I mean by this is that like in a system like Coq, because you have definitional quality and you use definitional quality for lots of things, there's pressure on the kernel to get more definitional qualities on things, and don't just implement things on top of the existing features. Instead, build them into the kernel so that it can do things better and faster. I think that pressure is bad because it leads to increasing the size of the kernel over time, right? So Coq's kernel grows regularly because of these sorts of things. It gains bugs regularly because of these things. If you can have a system where you decouple these things, then you can have a system which is defined, put in a spec, implemented 1,000 times, and if you can verify it once, then like it doesn't keep breaking, right? And I think that this also affects how well the uninitiated can understand what we're doing, right? This is a very complicated activity, and the simpler we can make it, the better it is to understand. So I hope that Metamath 0 will bring a fresh light on these ideas, show people sort of what it can do, and build a good foundation for the next generation of ITPs. Thank you.